Oh, hello everyone, and welcome to this talk at the IEEE Census 2020. My name is Andreas Erbslöh, and I'm actually a PhD student at the University of Duisburg-Essen in Germany. Share my monitor. I have the great pleasure to present my work of the CMOS integrated spike detection algorithm for determining the firing rate of the retinal network. Let's start with a little introduction. Today, there are many implantable stimulators available on the market that counteract physical sensory limitations. For example, deep brain stimulation helps to compensate the motoric loss in Parkinson's patients, or the visual loss due to the retinal diseases like retinopathia pigmentosa. In a normal case, light transmits through the eye and will be observed from the photosensitive layer of the retina. The retinal network will process the visual information and compresses the data stream to the visual cortex. In the case of the retinopathia pigmentosa, a degeneration of the photosensitive layer is available. Electronic implants like the Alpha AMS from Retinal Implant AG stimulates the degenerated retina to restore a visual impression. These systems have the disadvantage that they only stimulate the neural tissue. And these stimulation parameters loses his effectiveness over the duration of use due to the neural changing. This effect can be reduced by implementing the concept of closed-loop stimulation, in which the retinal activity is recorded after the electrical excitation. This requires the implementation of a recording unit. And the main topic of this talk is the hardware-friendly feature extraction on the recorded raw data to determine spike activities in real time and on chip. This step or this technique can be used in future to tune the stimulation parameters. So for that, the stimulation setup is shown here. The tissue connection is done with a working electrode and the counter electrode. The working electrode is connected to the stimulation front end and also connected to the recording front end with the integrated biosignal processing. In the next minute, I want to present the CMOS design of an optimized spike detection algorithm, the SDA, and within simulation results, I want to verify the completely recording module, which includes of a low noise preamplifier and a comparator. After it, I want to show you how it is possible to record and stimulate the tissue simultaneously without any artifacts due to the stimulation. For our CMOS design, we have designed a variable A script for describing the retinal responses, which is required. This script includes the generation of the desired action potentials, the unwanted spontaneous oscillations, and the terminal noise of the tissue and the electrode interface. The origin of the oscillations come through the network remodeling of the retina due to the photosensitive degeneration. Here on the right, you see an example of the neuron output, which will be described now. You can see here the black line is the voltage of the action potential, which consists of the settled action potentials. The time shape of such a spike is programmed with a lookup table, in which the parameters of the amplitude and number can be set. The electrode voltage the red line is applied on the input of the LNA, and this voltage is the sum of the spikes and the oscillations which is approximated via some signals of sine waves. Now we come to the description of the firing rate measurement. This firing rate contains the number of detected spikes within one measurement period. Our approach is a hardware-friendly integration of an analog spike detection to measure the firing rate in a high-density electrode array for future retinal implants, instead of ADC sampling the tissue response and to perform the spike detection externally with intensive computing. In the neuroscience, the nonlinear energy operator is widely used for spike detection. This algorithm is a frequency-dependent energy detection. It results in a suppression of the low-frequency oscillations and in a high amplification of the fast action potentials. The formula you can see right here, but it's for the CMOS integration, it's too complex, needs high power consumption, so we must optimize them. By analyzing the complex Nero operator with raw data, we have found out that the first part has the most impact on the gain. To increase the gain and the stability of this algorithm, we have added an additional high-pass stage. With applying a sine wave, the output of the STA depends only on the amplitude and the frequency of the sine wave. The next step to measure the firing rate is that we converted the detected spikes into digital trigger pulses, and to count these pulses with an 8-bit digital counter. The CMOS circuit of the optimized SDA has been simulated in the analog design environment of the ASIC development program Cadence with the already described neural emulator. In this simulation, the script sets 92 action potentials, each with an amplitude of 80 microvolt. With a detailed zoom, the output of the SDA shows only strong responses in the presence of an action potential, and the oscillations has nearly no impact. And only to these timestamps of an action potential, a trigger pulse is available. The next simulation step is stability analysis to determine the true detection rate is done, in which the amplitude of the action potential has been switched from 10 microvolts to 60 microvolts. Also, the influence of the oscillation has been enabled and disabled. And the result shows that in both cases, a true positive rate of nearly 1 can be reached with amplitudes higher than 52 microvolt. And the false rate is constantly 0. Now we come to the CMOS implementation with a focus on the SDA and the stimulation artefact-suppressing technique. The optimized SDA requires a second-order high-pass filter, in the square for the energy detection of an action potential. The generation of the digital pulses is done with a comparator and a lossy integrator, which generates the trigger pulses with 2 mm pulse durations. The feedback resistor, RPA, consists of tunable high-resistance Seidl resistors. For the simultaneous simulation recording, these Seidl resistors are tuned to suppress stimulation artifacts. By using the pole shifting technique, the high-pass frequencies of the preamplifier and the first stage of the high-pass, or the first high-pass stage, are increased by decreasing the feedback resistance. This can be done by increasing the current tune of the tunable Seidl resistors. This leads to reduced sensitivity of the preamplifier to the stimulation signals, which are much stronger than the biosignals. Here are the simulation results of the complete stimulation setup, in which the current controlled stimulation excites the retinal tissue. The responses show only the X potentials, and there are only small artifacts at the high pass output of the SDA and the output of the SDA. These artifacts will be filtered out with the increased threshold voltage, which will be restored after the stimulation, so that the action potentials or the detected action potentials can directly detect it. Here in this case was only without oscillations, and in this case there were the oscillations available, but it shows the same effect. The same effect is achieved by using the pole shifting technique with the increased threshold voltage during stimulation. In the paper, you can find a GDT technique for a stepwise lowering of the threshold voltage, which is left out due to the short presentation time. To sum up, I have shown a CMOS circuit to measure the firing rate with a hardware-friendly spice detection algorithm, which is nearly robust against stimulation artifacts by using the pole shifting technique. This module is part of an 8-channel prototype for closed-loop stimulation, in which each electrode module includes a stimulation front end and a recording front end. In the future, this prototype will be optimized for further research projects in which new implants concept with high density electrode arrays and the adaptive stimulation will be developed. And clearly, this work will be tested biologically. Finally, thank you for your attention, and now I'm available for your questions. Thank you.